Jansson. I will talk about level P complexity Boolean functions. First, let's say that this is joint work with Julia Jansson, and she's actually my daughter, so it's an unusual kind of internal paper. And the story of the start of this paper is that she was writing a master's thesis at the math department, and I read a draft, and there was somewhere in this thesis a polynomial of 8th degree, which was supposedly the minimum of like billions of polynomials, and there was some two-page argument for why this, due to symmetry and whatever, was actually the minimum. And I was saying that, you know, if I computed an 8th degree polynomial and claimed it was the minimum based on only textual proof, I would not trust myself. Haven't you tried to compute it prove it in the computer in some way? And she said, nah, well, it's just a conjecture and it's not that important for the thesis. And I said something on the line of, well, it should be easy to do in Haskell. It wasn't, but it resulted in a paper anyway. So what is level P complexity? And I should say perhaps that the subtitle there, using thinning, memoization, and polynomials, that's basically what the paper is about. So algorithmic techniques for getting a completely untractable computation down to something you can compute in a second or two. So the level P complexity, I will go into details later, but you can already see some graphs here. There's some functions, some polynomials. The blue one starts at 5, goes down and up again. The dashed one starts at 2 and goes up, and they're actually sort of competing here in the middle. The p, which is the parameter for the polynomials, that's the probability between 0 and 1. And we will get back to the details later, but basically these polynomials are expected costs of evaluating a particular Boolean function, which is also listed there in the middle, and the whole concept of computing a level P complexity is taking the minimum of lots of these polynomials, billions of them often. Okay, so back to basics. What's a Boolean function? Well, it's a function from b to the power of n to b, where b is bool or bit, something like that. We could have the sim5 function from the previous slide, an AND gate, a majority on 3 bits, or the motivating example from that thesis, for which the polynomial was derived, the iterated majority on 9 bits. So you take the majority of 3 bits in 3 groups, and then you take the majority of the majorities. And this is like the voting systems in the UK and the US, so first past the post and so on. So you can win the election without the popular votes, if you win in the right sort of places. Okay, anyway, this Boolean function is just evaluated on an n-bit word, bool vector, and it can be evaluated in different ways. So we can capture an order of evaluation in this data type. This is a sequential evaluation, and this is a decision tree. So it has 2 constructors, pick, which chooses an index, I, for the first evaluation, and then has 2 decision trees, left and right, if you get a 0 or a 1 when looking at that first bit. And then it has the constructor res for the leaves, where you already know that the function is constant. So all the rest of the bits are irrelevant, and you can return a bool, true or false, or a bit 0 and 1. So on the right here, you see an example tree, which is for the majority on 3 bits, a very simple Boolean function. If you see 2 zeros, then you're done. You know the majority is 0. If you see 2 ones, then you're also done. And in both those cases, you only need to evaluate 2 of the bits. You only need to inspect 2 of the bits. Whatever the third bit is, you know who is 1. In the other cases, if it's 0, 1 or 1, 0, you actually need to inspect the third bit. And the average here, the average cost would be 2.5, but it would be 2 sometimes and 3 sometimes. And there are 2 to the n inputs to such a function, and we can compute the average, or in more general sense, we can compute the expected cost if we have some probability distribution over the input words. And for this paper, we talk about uniform distribution, independent for all the bits, but all have a probability p of being true or being 1. So you can go from a very low probability of 1s or to a very high probability and everything in between. And that means, if you want an example, for the majority, for the decision tree on the previous slide, and actually for all decision trees, this is the polynomial. So it goes from 0, 1, 2 to 2.5 and down to 2 again. So if you're very sure that the bit is going to be 1, you only need to look at 2 bits. Otherwise, in the average, it's 2.5 bits. So it's a bit boring for the majority because the decision tree doesn't matter. I should say also perhaps that the decision tree is a way of encoding a Boolean function, but there are lots of decision trees for the same Boolean function. So it has too much intentional information about the evaluation. Anyway, the expected cost of the sim5 function from the previous slide, it has these different polynomials. One is sort of very bad at the endpoints. It needs to look at all the 5 bits. And another one here is very good at the endpoints. It only needs to look at 2 bits. But they actually cross in the middle. So if you want to compute the level P complexity, that's defined to be the minimum over all these polynomials, then it becomes a pairwise polynomial function. In this case, it goes from 2 up to here, it goes down a bit, and then it goes down to the first function again. So that's the sort of thing that wants to be implemented. And I should say, I've never felt a big need for implementing the level P complexity for any function, but I thought it was an interesting challenge to see if one could do it for interesting functions. And for the sort of general algorithm here, the basic specification, you could say, is generate all decision trees for your function, pick the best one. Easy, obviously correct. Well, easy, I mean, you have to say how you generate them, and this is one example of describing it. So for every possible start position, for every possible start bit, generate 2 immediate subfunctions. So if you take the bit and then you set it to 0, you get a smaller function, or n-1 bits. And then you can continue generating all decision trees for that one. That will be the left subtrees. And you can set the bit to 1, and then you can generate all the decision trees for the right subfunction. And then you can combine them with a cross product in all different ways. So there will be lots and lots of trees. You can produce this in Haskell with some singleton sets and some other constructors. This is generalized a bit with type classes so that it can compute with the same code either polynomials, decision trees, or a few other things. So how many decision trees can there be? That was the source of my mistake that this would be easy. I thought, well, how many can there be? Well, actually, if we take a recurrence relation for the worst case, it has this shape, n times the previous size squared. It starts out nice with 1, then it's 2, and then it becomes the squaring of squaring and squaring and squaring, and always multiplied by n as well. So it's doubly exponential. It grows ridiculously fast. So there are basically far too many such functions. You cannot compute the minimum by just generating all of them and then looking through it linearly. So what can we do? Well, first step is to see when we compare them, we want actually to look at the polynomials, when we compare the decision trees. So maybe we don't even have to compute decision trees. We can directly compute polynomials. You can fuse these computations. And yes, we can push the computations of the polynomials all the way down into the recursive generation of these trees. So instead of trees, we generate polynomials. And why is it good? Well, for one, there are fewer polynomials than there are decision trees, and 2, they are easier to store. A decision tree is basically this 2 to the n, in worst case, tree structure, while the polynomial only is a list of a few numbers, integers. Okay, can we do some thinning? So thinning here is the idea of the fact that we want to pick a minimum element of a list after having generated that list recursively. Perhaps we can throw out some bad solutions already early on. Basically, yes, if we're careful, we can create an order here which is such that we can throw away polynomials for subfunctions which will never be able to compute to the minimum at the top level. So we may not be able to throw away everything, but at least we get a smaller set. And remember from the start, it could be doubly exponential in size, and it turns out it becomes much, much smaller for all the cases we've tried with this. Are we done? Unfortunately, not quite yet. So we can easily compute n equals 5, 6, perhaps 7, but n equals 9, so 9-bit functions is still beyond reach here. And we wanted this iterated majority example. And if we then start exploring, we realize that this recursive generation of polynomials now, it was decision trees first, it calls itself recursively 2n times at the top level. So for n equals 9, that's 18 recursive calls. Each of those calls will call 2n minus 1 times. So that's 16 times 18 calls, and so on, we get roughly 100 million recursive calls for this computation. And that's a bit much. So that's why I started the computation one evening. It wasn't done in the morning, and I thought, okay, we have to continue the work here. Then the next question is, maybe many of these calls are to the same input. And that's true. So we can use memoization. So remember the hello world example for memoization, which is the Fibonacci sequence. If you want to compute the Fibonacci, then you have two recursive calls, and if you're not clever, it will basically take the number of steps to compute it as the number you compute at the end, which is exponentially growing. So it's very stupid. And instead, you just compute them from bottom up. So we could think here, maybe we want to compute all the Boolean functions and their complexities on the way up. But already Boolean functions are doubly exponentially many. So that doesn't work. But we can build a table while computing it. So we can fill in only the functions we actually run into during this recursion. And it turns out of this 100 million calls for this motivating example of iterated majority, there are only 215 distinct subfunctions encountered. Okay, well this then, it takes just a second or two to compute the level P complexity for this function. And you might wonder, why not a millisecond? And the thing is that we still have 100 million recursive call. It's just that most of them are a lookup in the table. Well, most of them are find out if we've already stored the function. So compare two functions for equality, and then look up the thing in the table. So what have I glossed over to fit this in a 15-minute presentation? Well, the actual implementation of memoization is a bit tricky. We need to compare functions for equality, and that's usually not very good. I mean, these are finite functions from a number of bits, but still, if you would compare all the outputs, that's 2 to the power of n of them. So you don't want to compare them in that way. But fortunately, binary decision diagrams encode Boolean functions very efficiently and uniquely, so you can compare them syntactically for equality, basically. Then polynomials. When you want to find these piecewise polynomial functions, we have to find polynomials intersecting. And it turns out it's not enough for the n equals 9 case to compute with double precision. You actually need basically exact solutions of these equations. And what that entails is that you actually need to compute symbolically with algebraic numbers. So algebraic numbers, if you don't remember, that's basically roots of polynomials. And you can add, you can multiply, you can do all kinds of nice operations on these algebraic numbers if you encode all this structure. You need to do root counting, factoring, GCDs, and so on. And that's actually the state of the published paper. And then I had a presentation locally at Chalmers, and I had this challenge saying, well, you know, it wouldn't be fair if we can't do the 3-level iterated majority on 27 bits. But it was completely out of scope for the current setting. And then Christian Sattler and we were sitting down and doing some work on this, and actually using some more properties about these classes of Boolean functions, we could actually get it to much higher levels. But that's actually not published yet. The code is on GitHub if you're curious. Okay, conclusions. If you run into an intractable problem and you have happened to say that it should be easy to solve in Haskell, maybe you should look for some algebraic simplifications and things, like thinning to reduce the size of the sets you're computing, memoization to make sure that repeated calls don't need to be recomputed, representation of functions, here both the Boolean functions using BDDs, which are roughly decision trees with sharing, so not decision trees, but decision graphs or decision DAGs. And then finally, polynomials and exact computation with polynomials really helps the complexity down in this problem. Okay, so the paper, as I said, is online. The code is on GitHub. It's a joint work with Julia, who is now a PhD student in the mathematics department, not with me as a supervisor. Questions?
Hi. I had one question. You said that there were like 100 million recursive calls. And then if you memoized it, you still had 100 million like lookups into your memoization table. That kind of surprised me because, I mean, with the intuition I had, I think that, okay, if like at the first level of iteration, you look something up in your memoization table, it's already there, then all the recursive calls that would make are ones that you're no longer making. That makes sense?
Yeah, but when you want to compute, before you have filled in that pot, you have to do all the recursive calls underneath it. So yes, there might be fewer than 100 million, but it's still on the order of 1 million. So most of the computation is actually exploring to fill in the table. So even if it's only 215 values that end up being needed there, you have lots of sub-computations to compute it. But yes, it's not 100 million anymore, that's true.
Thanks.
Go ahead.
Yeah.
Go ahead. Oh, sorry. There are two. Well, let's start with you.
Okay. So, had she found the correct minimum?
No. I mean, it was 4% difference, so I don't think it matters much. But it was a conjecture that this was the minimum one, and there was like 2 pages of reasoning why it should be, and the reasoning was between 4 different candidates, which for symmetry reasons ought to be the right ones, but none of them were. The solution was actually not very symmetrical. So an interesting detail here is that normally when you do BDDs, you just pick an order of variables, and then you always look at each layer is just one variable. But the solution has, it goes different ways on true and false sometimes. So the order is not enough, so it actually explores the tree in a more sort of clever way. I don't know. I haven't explored it further. Thanks. Yes?
Yeah, so my question is actually about variable ordering. So are you assuming a fixed variable order, or doesn't it matter?
Well, for the representation as BDDs for doing the memoization, yes, we just use ascending order for the variables. But the decision trees, they explore all orders.
Right.
So not even all orders. I mean, you can have different variables looked after as true and false in your subtrees.
Makes sense. Thanks.
And that sometimes matters.
All right. Thank you very much.